A warm welcome to you all to this wonderful afternoon. The topic of today's talk is a finite discussion on the infinite. As we all know or would have experienced, anything that is finite or infinite, whether it's a thing or an idea, both equally disturb us. And anything between the finite and the infinite can be more easily comprehended. But anything that comes in this realm of finite and infinite, it's always a world of charm. So, on behalf of the Planetarium, we extend a very warm welcome to you all to this wonderful talk, which is going to be given by Professor Tanvi Jain. And I now request Professor Gopakumar, the Director of ICTS, to say a few words about the activities of ICTS and also to welcome you all on behalf of ICTS. Professor Gopakumar.
Thank you, Dr. Madhusudan. Yes, I will add my welcome to all of you for coming here for this talk. And I'm especially grateful to the speaker, Professor Tanvi Jain, for coming from Delhi and giving us this talk. She will be visiting the ICTS also and giving additional technical colloquium there. So ICTS is a research institution. For many of you now, I think, are regulars at KAAPI with Curiosity. You've heard me say this a million times, but ICTS is in the north-west of Bangalore, and we have researchers in a variety of areas in mathematics, theoretical physics, quantitative biology, and going ahead probably computer science and so on. We also have a lot of visitors, which is why the I in ICTS stands for international. We are an international center for theoretical sciences. We have scientists from all over the world coming and spending extended periods of time at ICTS for various research programs. And if you look at our webpage, you will see a list. At any given time, there will be always a program going on in one of the areas, sometimes more than one program actually, going on in various areas of interest to researchers in India. So that's one thing we do, and our research itself is something in which we aim for the highest excellence. Finally, we also do a lot of outreach, and KAAPI with Curiosity has been our flagship outreach activity, which we have been holding for the last almost 2 years. October next month's KAAPI with Curiosity will be the second-year anniversary of the event, and we have Professor Vijay Raghavan, who was earlier the head of the NCBS in Bangalore, but is now the principal scientific advisor to the government. He will be giving a talk in next month's edition. But this monthly activity has been, I think, very popular, and I don't need to tell you people because you have probably come for many of our events before. So that's something we are very happy to be doing in cooperation with the Planetarium. We also have a lot of other public events and lectures, many of them at our institution itself. So once again, you can either sign up for our newsletter and to be on our mailing list for some of these events if you are not already on it. Of course, you can always check our webpage. And finally, if you would like to see some of our past lectures and events, you can look up our YouTube channel, ICTS Talks, which contains all the archived talks in KAAPI with Curiosity, other public lectures, various of the technical research programs, and so on. So there's a lot of material there, which is, I think, a great resource, and a lot of people are using it. And if you're a person who is interested in aspects of science, I'm sure you'll find a lot of valuable material by the best scientists from India and the world. So I won't take much more of your time. I will now invite Professor Rukmini De from ICTS to introduce the speaker and start the event. Thank you very much.
I am delighted to introduce Professor Tanvi Jain. She is faculty at the Indian Statistical Institute, Delhi. She completed her PhD in mathematics from IIT Delhi in 2008 and did a postdoctoral research there till November 2009. She worked in Department of Mathematics, University of Delhi for a while, and now she is currently a professor at ISI Delhi. So her interests are vast. Her current research interests include matrix analysis, quantum information, statistics and symplectic geometry, spectral properties of special matrices, matrix inequalities, and perturbation bounds. Her postdoctoral research was in the area of topology that included the study of various hyperspace topologies on the spaces of set-valued maps. She has received the INSA Medal for Young Scientists in 2013, and she is an associate of Indian Academy of Sciences from 2010 to 2015. So it gives me great pleasure to invite her for the talk. She's going to give a finite discussion on the infinite. Before we start, I would like to invite Professor Rajesh Gopakumar to hand over a memento to her.
Good evening, everyone. I'm really delighted to address, to talk in this KAAPI with Curiosity lecture. And I thank ICTS and in particular Professor Rukmini Dey to invite me here. I'm used to give many technical talks, and it's really a pleasure to talk in front of a general audience and a bit non-technical talk. Now, here, as the title suggests, we'll be discussing something on the infinite. And as we have just 1 hour or so, a finite time, so I'll be talking about some particular, so we won't be able to talk about the whole of infinite, but I'll try to give you an idea what is infinite from the mathematical point of view. When we hear the term infinite, what is the thing that comes in our mind? So as soon as I'm talking of infinite, there would be a mental picture in each of your minds that this is something that's infinite, that maybe it's something that's not comprehensible, or it's something like that doesn't have an end. Like now if we think of universe, it's finite or infinite, but it will give us a notion of infinite. If we look at the night sky stars, and we cannot count them, the clear sky, it will give us an impression of infinite, that we are not able to count. So something that's endless, something that's not we are able to not count. Or if we look at the ocean, that will give us the depth of the ocean, how is it. Now these are the things that give us the notion. So again, if we look, so if somebody in fact is stuck in the forest, for example, a hypothetical situation, in that case also, it will look like to be an endless thing that is just continuing on and on. Now these things we are not very much concerned about, are these really finite or infinite? But these things give us an idea of that these are infinite, yes? But are these really infinite, or exactly what is finite, what is infinite? So let's look at two very well-known examples, and then we'll ponder upon that. So the game of chess was introduced by the king's vizier in his court, and the pleased king asked the vizier to ask anything. Now the vizier was, obviously he introduced the chess game, so he was a clever guy, and he didn't ask for the normal things that the king would have expected. So he didn't ask for diamonds, he didn't ask for gold, he didn't ask for land, but he just asked for a very simple thing. He asked for grains of rice. But again, he was a bit mathematical, and he asked the grains of rice in a particular manner. So now you all know that the chessboard has 64 squares. What he asked for? So he asked that for one square he wants 1 grain. The second square he wants 2 grains. Then the third he wants 4. And the number of grains that he wants is doubled with every successive square. So the last square of the chessboard, for that he wants 2 power 63 grains of rice. Yes? So now the total number of grains of rice that he has asked for is, that is, if we denote by S, that is 1 plus 2 plus 4 plus go on 2 power 63. Now what is that number? So these are 64 numbers that we are adding, and a very simple trick to add this. So we just consider twice. So we just consider twice of S, and that is that. So 1 plus 2 plus 2 power 63 becomes twice S is 2 plus 4 plus 8 plus 2 power 64. And now we write S in below that, a little shifted to the right, left. No, but for the first square, there's just 1 grain, so 2 power 0. 2 power 0. The first square is 2 power 0. So 2 power 1, 2 power 2, 2 power 63. 0 to 63 it's basically having. 0 to 63 we are having. So therefore now we have 2S, and we write S little shifted to the left, and as we write you can see the 2, 4, all these coming below one other, and if we now subtract, all the terms cancel. We can very clearly look at that, and only 2 power 64 and 1 remain. So I have S as 2S minus S, that is 2 power 64 minus 1. So what is that number? Now if we compute that number, this is exactly a 20-digit number that is displayed on the screen. So, and this number in fact is, so these many grains of rice and these many grains in fact exceed world's total production of rice. So now this is something that's, anyways, it's not possible or practical to give a person to another person. So is this infinite? Okay, we'll leave the question here and we go to the second example. There's a legend that says that at the time of creation, Brahmaji put 3 needles in a temple of Banaras. So he put 3 diamond needles, and around one of the needles he had put 64 gold discs. And in what manner? So 64 gold discs, they had different sizes. So at the bottommost disc is the biggest, then the smaller, and the topmost disc is the smallest one. So in the figure you can see that it's caused in a conical shape because the sizes are decreasing as we go up and up for the gold discs. And Brahmaji asked the priests of the temple to move the disc in a particular, following a particular law that he specified. And according to him, when they'll complete the task, so they want, all the discs, 64 discs, need to be moved to another needle. So there are 3 needles, around one there are 64 discs. So when all the discs move to the third needle or the second needle, another needle, then the universe will come to an end. So that's a legend. And what are the laws? Let us just see the laws also that he specified to the priests. So the laws say that one can move only one disc at a time. So from any of the needles or at any point of time I can just pick up one disc, and that too also the topmost disc, whatever there is in the needle. And also at no point of time the smaller disc can be below the bigger one. I cannot have at any point of time, I cannot make a move that makes my smaller disc below the bigger one. So these things one has to keep in mind. So this is in fact, you would have played the game of Tower of Hanoi, or you would have heard the thing. So, and this is very well known for the algorithms in computer science. So, but let us see if that through a toy example, how does it work. So as it will work with 3 discs, the same working is there for 64 discs also. So if we understand for 3, we will be understanding for 64. So here we are having 3 discs in one needle, and now we are just allowed to move one disc, and so basically we will just obviously the thing is we will just take the topmost disc and put it in the 3rd needle, for example, and then we put the 2nd disc from the 1st needle and put it in the remaining 2nd needle. And now because my bigger disc cannot be above the lower one, so only move that I have is I have to move the smallest disc that was in the 3rd needle to the 2nd one, and then I'll do the largest disc to the 3rd needle and do a similar thing and move the other 2 discs to the 3rd needle. So basically one thing that one should see here, what I have done, I have first moved 2 discs, so as to say, 2 discs and arrange them in the 2nd needle, and then I move the 3rd one. So it's kind of a recurrence relation, a recurrence procedure that I am following. So now if I have to do for 4 discs, what I'll do? I'll first have the 3 discs arranged in one of the needles, and then move the 4th one, and then again arrange the 3 discs above the 4th one, biggest disc. So that's a recurrence relation, and I suggest that you should go and actually check it out. That's a very simple mathematics, and so one can really check it out. And here, so we have the number of moves that will be required. So one can see if you have 2 discs. So in the previous diagram, in fact, you could see if so the 2 discs require just 3 moves. So as the 2 discs, having the 2 discs in the 2nd needle, just require 3 moves, and the moving 3 discs actually required 7. So this is basically 2 to the power 3 minus 1. As we will go on, my 64 discs, moving the 64 discs will require 2 power 64 minus 1. And again that's the same number S, if you remember that Wazir wanted those grains, the number of grains that Wazir wanted. And these are again that 8-digit number. But now here we are a little interested with what time it will take. So if we assume that, okay, no one priest can do, but if the thing is, if we continue doing this, moving the disc without a break, so there are priests who are doing this without break, and they just take 1 second to make one move. In that case, how many moves we can have in 1 year? The number of seconds in 1 year? Yes? So that is just the number of days multiplied by number of hours in a day, and multiplied by number of minutes in an hour, and multiplied by number of seconds in a minute. And that comes out to be this number. Now I know how many moves I require, and now I know that how many moves I can have in 1 year. So I can calculate the number of years that will be required to make all the moves. Yes? And that comes out to be something that is more than 50,000 billion years. So maybe So maybe maybe again the universe comes to an end by that time or before that. But still, so now is it, so it's something that almost seems to us endless. The previous example seems to us that, oh, that's something that's very, very big. And here it's seeming to us that it's not going to end. It's going to end with as the universe ends. So are these infinite, so as to say? So still now one can see that this, though I have a 20-digit number, that S, but still I can get a bigger number from than S. And in fact, I can get many, many numbers bigger than S by just adding zeros in front of it. So I can have, so is this really infinite? The question still remains. Now one aspect that we had, so now that when we think of infinite, the stars that we are not able to count. Here we can see that, okay, it will take us more than 50,000 billion years, but still will be, so it's okay, it's not practical maybe at this point of time, maybe, but at some other the science is so developed that maybe it becomes practical to count that S, to have those moves, to produce that much of grains of rice, and to give somebody to that many grains of rice. Maybe that science is so developed. So is this really infinite? Now we come to another aspect of infinite that we have in our mind, that it's something that's not, we are not able to count. Maybe in practically, maybe, but at least we have this notion that we are not, this is something that we are not able to count. So now, but if we are not able to count it, how will we understand it? And that's why probably we say that it's something that it's beyond our understanding. It's incomprehensible. So is it really incomprehensible, or what do we do? So now the question is that if we do not know counting, then how do we manage things? So maybe our ancestors, if they did not know counting, how will they have managed? So now there's if you meet a person, for example, just think, and he doesn't know counting, he doesn't know even 1, 2, 3, 4, 5. How will you tell him that there are equal number of fingers in both your hands? Just think, how will you tell him? One-to-one correspondence. And how, what basically, so what will you mean by that? So how will you, basically how will you show me, I don't know anything, I don't know one-to-one correspondence also. So basically you'll do this. I'll say that, oh, for every finger you have, for one hand you have the finger of the other hand. Yes, that's exactly you will do. And that's a smart way and the simplest way to do that. Yes. So remember that you will do this, and I've got the thing from you. Now, okay, I give you another situation. I give you another situation. There's a farmer who has, now we know that there are 30 cows, but he doesn't know he has 30 cows, because again he doesn't know how to count. And he leaves his cows for grazing in the morning and takes them back in the evening. He cannot be a policeman seeing the cows, every cow, watching every cow where it goes throughout the day. So he's just, now at the end of the day, he wants to ensure that all his cows are back, no more, no less. How will he do that? How will he feel his cows? And how, so that will need a really good sense of touch, that just by feeling he will know that these are the exact number of cows, he has not felt any less. So what do you mean by every cow must be in place? That means? Yes. So, okay, that's fine. But so I got an answer from that every cow should have something to tie. So basically, what are we doing here? We are having, so there's something to tie, so we have a pole. So basically what we have done, for every cow we have a pole assigned, and exactly that, so one pole for one unique cow. And remember, it's not necessary that the first pole is for some specific cow. It's just that I have, for one cow there is a unique pole and vice versa. For one pole there is a unique cow. And now when the cows return and he ties them, then in that case, he'll now that if the pole is remaining empty, he knows that the cows are less. If the pole is all poles are occupied and the cow is left, he knows that some other cow has come. So then he'll maybe use his sense of touch and all those things to feel his cows. But at least he'll know by that number that yes, this is the way that he. So what is the thing that is coming into picture that is playing the role in both the examples? So, correspondence, yes. So we have a one-to-one correspondence, and how do we so now just we formalize that how do we really define? So if we have two collections or two sets, if we are, so and for every member of one set, we have a unique member of the other, such that no member is left unpaired. That is one-to-one correspondence between the two sets. And as we had seen in the first example, now if I have one-to-one correspondence between the fingers of both my hands, I know that both hands have equal number of fingers. So in fact, if two sets are in one-to-one correspondence, they have the same number of elements. That you all agree, that's a simple fact enough, isn't it? So now that we are all agreed upon till this much. Now see, earlier our ancestors maybe wouldn't have known how to basically count. That notion of counting. So exactly what are these numbers? These are just symbols that first they were counting through one-to-one correspondence through poles or pebbles or something, so by fingers or so, and then they started giving the symbol or specific term to it. Yes? So they would have said, oh, this is 1, this is 2, if I have this 3, this is 4, and so on. So this is the way that maybe the numbers would have developed. So now, okay, so we know now counting and all those things. So what exactly? When I say that the number of fingers in our hand are 5, or when Manjunath the number of cows that Manjunath has are 30, what do you mean by that?
Countable.
What do you mean by countable now? So no, but exactly what do you mean by that? How do we basically understand? Now we have come to the notion of one-to-one correspondence. So how do I say that the number of fingers in my hand are 5 but not 6, but not 7? Okay, they would be finite, infinite, but how am I sure that they are 5, not 6?
Because a certain number has been allotted a symbol.
Yes, and that certain number has been allotted a symbol, and also what I am doing. Now for I have this hand, and I say that I am mapping this finger to 1, I am mapping this finger to 2, this to 3, this to 4, this to 5. Maybe you can say that I allot this to 1, this to 2, 3, 4, 5. But what am I doing? When you count, when a kid counts, the first thing that we all have done in mathematics, we are given a book and say that, oh, count the number of objects. You put a finger on the object and say, this is 1, this is 2, this is 3, this is 4, this is 5. So aren't you doing a one-to-one correspondence between those set of objects and the numbers, the set of numbers? Yes? So exactly now the notion comes that what is my the number of, what do I mean by a particular set having this many number of elements? Is basically that particular set is in one-to-one correspondence with that particular set of numbers. Yes? So if it has 5, so I have 5 fingers, that means I have one-to-one correspondence. The fingers of my hand are in one-to-one correspondence with the set 1, 2, 3, 4, 5. Exactly. So now coming to the mathematics, a very simple mathematics thing. So here now mathematicians, how do they define finite set? So if we understand finite set, we'll be able to understand infinite set. So let us just clarify our understanding of finite set. So finite set is a set which is in one-to-one correspondence with the collection of numbers 1, 2, 3, n. And that n now can be any number. It can be 1, it can be 2, it can be 3, 5, 10, 100, million, 10 million, 2 power 64, 10 power 64, anything. Any number you can think of. So now it can be really big, it can be that S, but so now you know number of grains, what are those? The number of grains that Vizier asked for. Finite. The number of years or the number of moves or the number of seconds that the priest will take is finite. Though they are big, though they are endless, but they are still finite. So at least we are settled upon that. And now what is infinite? Obviously that is which is not finite.
Finite is not very clear. I just defining what this point.
Huh.
I feel finite has an element of time required to count also.
No, the mathematical sense is basically exactly this is the thing that though, so now one can say that I have told you infinitely many times this thing, but so generally when we talk to our children we say, I have told you infinitely many times but you don't understand. But now this is not the thing that it's basically that's the notion of our mind that's telling me I have told so many times that I cannot tell more, or one cannot just comprehend how many times I have told. It can be 10 or 20 or 30, but that also can look to us as infinite. But that's just the notion of our head. That's not a mathematics. So that's a general notion that we all have when we use the term infinite. But infinite is something not exactly that we use. So that's exactly I'm saying. Now the number of grains that Vizier asked, that exceeds rice total production. So obviously nobody can give to the other person. But still mathematically they are finite. Yes?
You cannot define the process of counting as a one-to-one correspondence with a set of numbers 1, 2, 3 up to n, correct?
That is exactly you have the process of counting. Right. This is the way that we define the process of counting.
Right. So my question is, similarly, can you give I mean, what does it mean to say that something is bigger than something? 5 is bigger than 4.
5 is bigger than 4.
Yeah, I mean, like in the days before people knew counting, so would they have understood what 5
yes,
that 5 is bigger than 4?
There are two notions when we have numbers. So one is the size of the set that I'm basically basically on. The other is the order of the set. So maybe that we can take up after the talk. So that is something, the different aspect of numbers itself. That when we are talking of the order of the set. So here you'll see later on it relates to cardinal numbers, and the other notion is mathematically called as the ordinal numbers. So order of the set. That will basically come, we can discuss it after the talk, but because it's something that's not the focus of the talk. Okay. So this is something that we are talking from, again, because we have some limited, so we are just it's not, the talk is not something that covers all the aspects of infinite. That's not possible. That will take a long, long time, or many, many lectures. But we're just concentrating on one of the aspects of infinite, in fact, or finite, or because we're talking of finite, infinite, we are naturally talking of finite. So mathematics, it's though, exactly, that's the thing, that though we think that infinite is something that's not practically counted, I cannot, that's impractical to count. But no, for mathematicians, this is not the case. So we use the word infinite, in fact, generally for what is finite. But only the thing is that we cannot describe how many times or how much time it will take, so that we just call it as infinite.
Basically, when we are lazy to count.
or in that case, maybe the king is not lazy to count, but he is not able to count. But sorry?
Inability to count. Inability to count.
Yes, inability to count. That's a human inability. So that maybe the science has developed to that extent that maybe we will be able to count it. So at some point of time, it's basically that we are not so much developed that we can count that. Now see, if you go down of rice, you'll feel that, oh, it has infinitely many grains. But that I can really count. I can have at least an estimate of how many grains of rice it has. I can just take a handful and just measure them, just weigh them, and see that how many grains, and then I can just, from the volume and all those things, I can just have an estimate at least. But that also looks to me as infinitely many grains, isn't it? So, yeah. So something that's, I hope that's at least that's acceptable, that finite is something that is in one-to-one correspondence with a set 1, 2, 3, 4 till n. So we are ending somewhere. I'm not talking of practicality of whether we can really count, we can have that n. Okay. I'll show some examples also, and then, so an infinite set, obviously that's something that is not finite, is infinite. So that's a simple, so now the question arises, so you will ask, I have said that, oh, the number of grains is also finite, something that maybe we are not able to count is finite. That all those years it will go to the end of the universe, but still it's finite according to me. Then is there anything infinite? Is there something that is infinite? Can you think of?
Anything that does not have an endpoint, like for example cells that keep dividing again and again, like meiosis. Anything that keeps dividing further on and further on. Like for example, biologically cells, when they undergo meiosis, they split into 2. And each cell then splits into 4 and 8 and 4 on.
So
there is no
end point. An infinite time.
Yeah, they will go infinite. So there's no end point.
Because I am a little ignorant about that thing. So yes, if it is good for continuously without an end,
yes,
then it will be fine.
Unless unless there's an external force that stops it, naturally there is nothing that stops it. It will keep on. We actually do say it's infinite. So that set does not contain it, right? I mean, because unless you stop it, it's going to keep going till the end. There's no end for it. Yeah, but how will you count? Because by the time you finish counting, already another 4 cells have divided.
Yeah, so actually, practically it will have an end. And therefore, so now for example, what you're saying, it will have first 1 cell, and we start with 2, 4, 6. It's exactly the exponential growth kind of thing that we're talking here. And it will, because there will be some external force, and that will end. So it will be finite at that point then. It can be a very, very big number.
If there is an end, it'll be, as you said, it'll be a big number.
It will be a big number,
but you're talking about a point, yes, where it stops.
Yes, so it won't be infinite in that case. Yes, so exactly. Now this is something that we talk of when the space is, so the time is infinite. So it has been there and it will be always there.
And integers, numbers.
Yes, that's a very good point, and that's a very mathematical answer you have given.
Here, I want to add one point. Because especially discussion, not just a talk.
Uh-huh.
Now, when we say it is not finite, therefore infinite,
Yes.
it appears there are two sets. Set A, if it is not in set A, it is set B. They don't have intersection. They are not complementary. Actually, here, finite is encompassed in the infinite set.
Yes, it's a
However,
subset.
there is no set can ever encompass the infinite. Infinite is a set of things which can never be encompassed by anything else, but all others are subsets of the infinite.
No. That also we'll talk about. Okay, so the example now, okay, so we had defined, let's come to, so we had defined a set of, you know all the set of natural numbers or integers if you're more familiar with. So 1, 2, 3, 4, and just keep on going that. Don't end at any n. Don't end at 2 power 64 or anything.
Just like a prime which is the prime number, because it is infinite prime.
So what do you mean by infinitely many primes?
Because we have detect them.
Exactly, we'll come to that also. So now if we come to our mathematical definition.
To properly, let's let her speaker go on at the end.
So let us go to a mathematical sense and say that somebody said yes. You said the set of integers is infinite. Now he said maybe the cells, but that will end. So he also accepted it will be a big number, but not infinite. Now if we come to the mathematics, how did we define finite set? That is in one-to-one correspondence with some set 1, 2, 3, 4, n. Now if we look at, so you all would be able to make a mental picture of, just collect all the numbers, 1, 2, 3, 4 and so on. You won't be able to write them, but you can have a mental picture in your brain, you can have that. And can you just think that we are not going to any mathematical technicality, but can you just think that you can have a one-to-one correspondence of all numbers with a particular set 1, 2, 3, n? Oh. This is the line segment. How is that happening? I don't understand.
You are now in the infinite sets exist to infinite sets exist.
This is a slide. So now see, can you really have this in, if you try to have that n for 1, 2, 3, 4, n, you'll see that if you just take 10 million, I'm giving a very non-rigorous, non-mathematical kind of thing, but just think that if I just choose 10 million to be the thing, then my number, I can have one-to-one correspondence for 10 million numbers. But then what about the 10 million 1, 10 million 2, or 10 billion, or 10 trillion? There won't be any pair for that number, isn't it? So we won't be able to have one-to-one correspondence of the set of all natural numbers with the particular set 1 to n for any n. Yes? So that's something that's infinite. And that also is very well, it fits in with our notion of big, endless. No, we are not able to count. Now no science can give me the ability to count all natural numbers, anything, how much science I develop, but I will never be able to count all the numbers. I will never be able to write all the numbers. So this is an infinite set. Now a little more, that's something that we are more familiar with. And that's again something that we don't think of. Just a line segment 1 centimeter long. It's not a big set. It's not that something beyond our comprehension. But still I claim that it's an infinite set. Because, so now in schools you would have read, what is a line? It's a collection of points. A point is something that has no width, no size, no depth. So, and how many points will a line have? Those are infinite.
But still, intuitive for me, a 2 centimeter line line has twice the number of points than a 1 centimeter line.
No, that's also not true. So that also is something that will be covered in this talk. So all the intuitive arguments, so now maths can be very, very counterintuitive also. So nobody can just think that, oh, this is my intuition and this will be true. So this is something that maths, here you should be aware, careful about. No, it doesn't have limited. What are the, so how many points will it have? Can you think of? Huh? See, if you're convinced about the line, circle, I just cut off 1 point. I just do a very simple thing. I just cut off 1 point from the circle and extend it. Just take a rope, tie it, it will become a circle. Just open that knot and you extend it. It will become like a line segment. Yes? So, in fact, circle and line segment have same number of points.
I think the infinite concept is closely related to the infinitesimal.
That's a different, yes, that's yes. You can note down the, yeah. So, now, so as we are not very much ready to accept the concept of infinite, similarly, our ancestors were not very much ready to accept the concept of infinite. In fact, they didn't accept, they didn't know, they just considered. So there's a thing. So now somebody said prime numbers are infinite. And interestingly, it was proved, and the proof in fact was given by Euclid, and that proof is such a nice proof that it still works. We still follow that. But he didn't accept, or he didn't know the notion of infinite. So what did he write? He didn't write that prime numbers are infinite. He wrote prime numbers are more than any assigned multitude of prime numbers. In simple language, if we want to understand, if I give you any n, for example, just for understanding, if I just give you that, I say that, oh, prime numbers are 10 million. He'll show you that no, they are more than 10 million. Or I say that, okay, maybe they are 1 trillion. Then no, they are more than 1 trillion. Basically, he's just saying that they are more than any number. But he doesn't accept that they are infinite. Okay, so like we are all, that they are more, but we don't accept. So this is a little earlier than Euclid, in fact. There was a very famous Greek philosopher, Zeno, who had given many paradoxes on motion. And all the paradoxes basically were because, so paradox is something that gives you counterintuitive. So it seems all fine, but it gives you some counterintuitive result. So, and that was because he considered space and time to be infinite, in the sense, now you are saying infinitely divided. So one of the just paradoxes, we'll have a quick look. So it's a very it's a well-known paradox. It's the paradox of Achilles and tortoise. So here what we have Achilles that runs as twice fast as the tortoise. So Achilles is a legendary Greek warrior, and now he gives tortoise a 1 kilometer start. So let us, for simplicity, let us assume that Achilles runs at 2 kilometers per hour, the speed of 2 kilometers per hour, and tortoise runs at the speed of 1 kilometer per hour, obviously. And he starts after 1 hour. So when tortoise has completed 1 kilometer. So now So when he'll reach, so that 1 kilometer start that he had given to tortoise, he'll cover in half an hour. And in that half an hour, tortoise will move forward by half a kilometer. Yes? Then that half kilometer he'll cover in 1/4 of an hour, 1/4 of an hour. And in that case, tortoise will move 1/4 of a kilometer, and so on. Yes? So Zeno claimed that in this case, Achilles will never be able to catch tortoise. Now, you all agree with Zeno? Yes? All agreed? No, the speed is fixed. Everything, the whole setup is fixed. Just imagine, you're all convinced that's good. So tortoise will never reach the Achilles will never reach tortoise. Okay.
The difference will be really less.
But he will never reach. So at least you all accept that the time, so here how are we divided? So how do I claim that the time and speed, the time and distance is divided infinitely? So just let us focus on that first. We have for example, let us take, we have 2 kilometer racing track. Okay. And now, so we have a point after 1 kilometer, have a point after 1 plus 1/2, 1 plus 1/2 plus 1/4, 1 plus 1/2 plus 1/4 plus 1/8, and it will go on. Yes? So it will there. So now you're all convinced that there are infinitely many points in a racing track of 2 kilometer long. So kilometer is just, so now I can, at least you are convinced that there can be infinitely many points in a line segment of 2 centimeter long, and similarly 1 centimeter long. Yes? And also time can be infinitely divided. We have 1 hour, we have half an hour, then 15 minutes, and so on. So my time also can be infinitely divided. But you all agree with Zeno also. So now what about in 2, so you all would be knowing, well, very, very basic, the speed, distance, time. What happens after 2 kilometers? So when Achilles starts, after 1 kilometer, after 1 hour, how much distance Achilles would have traveled? 2 kilometers. And remember, tortoise had started 1 hour before. So at that point, how much distance tortoise would have covered? 3 kilometers yeah. Are you sure? No, it won't be 3 kilometers. Okay, remember, tortoise is running at the speed of 1 kilometer per hour, and he is running for 2 hours. 2 kilometers. So now both are at the end of 2 kilometers. But now my question is, has not Achilles reached tortoise? So where is this? So this is the thing. This is the paradox, and basically what are you doing? You're having this distance, speed, time. Now these are, so you said that these are, there's a concept of infinitesimal. Here, when we're talking of speed, that here comes the distance of infinitesimal. That's basically a complementary notion of infinite. Again, so calculus is exactly based on the notion of infinite. But that will need basically a little more advanced lecture from this. So now, on the other hand, so now again somebody mentioned Anadi Anant. In fact, in ancient India, this concept, this is a very less known fact. So in ancient India, the concept of infinite was well developed. And in fact, not only that, so they considered space and time to be infinite. So anadi anant. So time is infinite. Anadi, it's from an infinite time and it will continue to an infinite time. Anadi anant. And so the earliest reference that I know of is a Jain literature by Pushpadan Budbali, Shatkhandagam, and 1st century AD. And there, they've not just considered infinite, but they also study different types of infinite sets. So Asankhyat, Anant, and there are different types. And that's in a way that has some correspondence with the modern notion also. Okay. So this was a brief digression to the history. Now we'll come to that is not intuitive for the infinite sets. So we had all agreed that if two sets are in one-to-one correspondence, they have the same number of elements. Now you can see, if you collect all the even numbers, certainly you will say they don't have odd numbers. So they have less number of elements than the collection of all natural numbers. But you can also see a one-to-one correspondence between the set of numbers and the set of even numbers. Yes? You all agree there is no mistake in this? So now you all agree that because you had agreed to me that if there is one-to-one correspondence, the sets have equal number of elements. So you all agree that now the set of even numbers and the set of all numbers have the same number of elements. You'll have to agree. Yes? So, and in fact, somebody also said prime numbers infinite. So, yeah, now prime numbers, that's something that I won't be showing you here. But prime numbers, because we talked about prime numbers also have the same size as the set of all numbers. So, in fact, now this is a characteristic property of infinite sets. I can define an infinite set like this, that if it is in one-to-one correspondence with a proper subset, then it is infinite. Every infinite set will be in one-to-one correspondence with its proper subset and vice versa. So if a set is in one-to-one correspondence with a proper subset, it's infinite. More particularly, if I drop some elements, some finitely many elements like 10, 12, 20, 100, I'll get a set, intuitively, obviously I'll get a set which is smaller than this set, a proper subset, but it will be having the same size that we call the cardinality, the same size as the given infinite set. So dropping some numbers, maybe they can be a million, maybe they can be more, but some finitely many elements doesn't change the size of the infinite set. Okay. And this notion was first noticed by Galileo, and he noticed it for the squares of numbers. So here you can see 1 is going to 1, 1 is going to 2 is going to 4, 3 is going to 9. So again, the square of numbers, the squares of all numbers has the same size as the set of all numbers. Based on this, in fact, there is a very interesting thought experiment. So I'll just have a very quick go through this. If I have a hotel and all rooms are occupied, and if you go to the hotel, what will the hotel manager tell you? All rooms are occupied, I'm sorry. I won't be able to accommodate you, isn't it? But now if there was an infinite hotel, and based on this notion, if you go to a hotel which has infinitely many rooms, and all rooms are occupied, but now the manager will be happy to receive you and request all his guests to move one room forward. And the first room is empty for you, and you can happily go there. And in fact, if infinitely many guests arrive, what he'll do? So you have a one-to-one. He knows, he's mathematical. He knows that there's a one-to-one correspondence between the set of numbers and between the set of even numbers. So he'll ask all guests to move to the next even number thing. So he'll guess 1 to 2, 2 to 4, 3 to 6, and all odd number rooms are empty. So now see, look, how good it would have been if it was practically possible that we have a hotel with infinitely many rooms. Now, you all know rational numbers, and so even numbers, though that was something that, okay, that was subsets. And now I go to a bigger set, and clearly you will think that rational numbers are more, so there are many more rational numbers than natural numbers. Yes? But again, that's not the case. So, huh?
It's just the same because everything's infinite.
That also will come at. So, and how basically, now you can see these arrows. So I can just assign my, so I can assign 1 to 1 by 1, 2 to 2 by 1, 3 to, I can just assign the sequence in which I am going, I can assign each natural number to it. And that's the way I can show that my rational numbers are, see, the number of rational numbers is same as the number of natural numbers. Now we come to, so somebody said, definitely the line segment has, 2 centimeter line segment has more number of points than 1 centimeter line segment. Again, that's not true. So here, what I am doing here, so you can see 2 lines, line 1 and line 2. Line 1 is of, let us say, it's 1 centimeter long. Line 2 is clearly, it's the double. It's 2 centimeter long, let us say that. And the dotted lines, because again, it's not possible for me to show infinitely many points, the correspondence. I've just shown the correspondence. So you'll get an idea how every point of line 1 can be mapped to every line of point 2, and no point of line 2 will be remaining unpaired. So we can have a pairing, can have a one-to-one correspondence between line 1 and line 2. So no matter it's 10 centimeter long, no matter the one line segment is 1 centimeter and the other line segment is 10 centimeter long. In fact, you would be knowing line segment and line. So line has something that doesn't have endpoints. There is a one-to-one correspondence between a line and a line segment also. Okay, so that's, and now somebody who knows function. So this is the function. So f of x by 1 plus mod x. So I take any point x on the line, x by 1 plus mod x will be representing the lines, point on the line segment minus 1, 1, basically. So that's also something that tells me that, oh, not only this and not only this, I can just collect all the points of a line segment and fill up, from those many points, I can fill up the 2D plane. Okay, so that's also possible. And so this is, in fact, this is true. So basically the number of points in a 2D plane are same as the number of points in a line segment. Also, so now something that, because we are talking of line segments and lines, if I give you a point, you cannot give me a next point after that. If you try to give the next point, I'll always have a point which is between them, because there are infinitely many points between any 2 points of a line segment. And similarly, so there are many examples. Now, one was thinking, oh, it's with this line segments, it's like that, but circle definitely has finitely, it's something that circle will not have that property. But again, the circle also has these properties. So any 2 radii circle I take, I have both the circles have the same number of points. So now the simple thing I have, one-to-one correspondence, I just start the line mapping, so from the center, I draw a radius to the bigger circle, and it will cut you at a unique point the smaller circle also and the bigger circle. That gives me the one-to-one correspondence basically. Okay? Yes?
So, for example, if I just draw an analogy, if I recall my physics correctly, in physics, when Planck made this assumption that energy is quantized and there's a minimum size of energy, and with that he then was able to, I think, get the Planck radiation law or something like that, if I recall correctly. So in this context, has anyone ever done some work assuming that distance is quantized? Like they assume there's the smallest unit of distance. Instead of assuming that point is of zero size, assume that a point is of some finite non-zero size, then would some interesting mathematics come out of that assumption?
I don't think so, but I'm not aware of. There are many very big physicists sitting here. I think they can better answer the question. You said it?
I think this question can be postponed.
Yes, yes. So those will be answered by a physicist then. Okay. And similarly, we have that there is a one-to-one correspondence between a circle and a line. So these again, the dotted lines show the correspondence between the circle and a line. So we just start with the North Pole and just go. So somebody said, obviously, what are you showing? All infinite sets will have same size. So do really all infinite sets have same size? That's also not correct. So now one way I was saying, this has same size as this has same size as this, but now I say, no. You see, in my examples, there was a very prime thing missing. I never compared the natural numbers with a line segment, because they do not have same size. So the set of natural numbers has the size of the set of natural numbers is strictly less than the size of the number of points of a line segment. So there are, in fact, now if I map, so if I have number of functions from a line segment to a line segment, so I calculate the number of associations I can have from points of line segment to the points of line segment. They are still more than the number of points in a line segment. So there are at least 3 types of infinite: natural numbers, lines, and the number of functions from a line segment to itself. In fact, you give me any set, any infinite set, I'll give you a infinite set which has size strictly bigger than it. Your power set, the collection of all subsets of a set. If you take, so for example, I take the set 1, 2. The power set will be empty set, 1, singleton 1, singleton 2, and the whole set. There are four elements in the power set. So always, the power set of a set has size strictly bigger than this. So there are infinitely many kinds of infinite sets, in fact. And so this is a very interesting mathematics, so as to say. Now the thing comes, you would have more seen the symbol infinity instead of talking of infinite, but everybody probably would have seen or heard of the symbol infinity, this horizontal 8 kind of thing. So what does this basically signify? This doesn't signify, so now one should be careful. This doesn't signify the size or an infinite set or an infinite number. This just signifies that something is going large and large. That all of us have the concept of, that n is becoming large and large. It's becoming 2 power 64, 2 power 65, 2 power 67. So I will say that it's going to infinity. So that is the infinity here. It's not basically taking an infinite value, but it's going to infinity. It's becoming larger and larger. And that was introduced by John Wallace. On the other hand, if I'm talking of different types of infinite sets, I should have some symbols to represent them or the sizes, their sizes also, and that we call as infinite cardinal numbers. For example, if not, see, this is a continuum that's basically the number of points in a line segment, LF2, and we can go on LF3, LF4, LF5. So, in fact, so we should remember now this all theory, modern theory of infinite sets, though it took long time, nothing is developed in one go by one man. But Georg Cantor was the person who formalized these, developed this notion, formalized these notions of infinite sets, and gave the notion of infinite cardinal numbers, developed, in fact, there's cardinal arithmetic on that. Infinite cardinal number. Thank you. So maybe we can look at address the questions after the talk. It's just going to end. So now the question arises that the thing. Now, if we understand what is infinite, the question arises where these infinite things occur. And you see that we all are using infinite, but without realizing that. Everybody knows that area of a rectangle is length cross breadth. Everybody knows the Pythagoras theorem. For how many rectangles it's true that area is length cross breadth? All rectangles, it's not for 10, 12, 20. And the number of rectangles that we can have will be infinite. So generally when we write a statement in mathematics, a theorem, that's true for an infinite set. So similarly we have, and not only that, now you would have all seen log tables, log x, pi you all would have seen. Pi, e, exponential, sine, cos, trigonometry. So what are the values that you use? You use pi to be 3.14, 142, 1415. You have some log 2 is 0.3010. But are these actual values? Exactly, is log 2 is equal to 0.3010? No. These are just the approximations. The actual values, in fact, come from they are a result of infinitely many operations. For example, you can see here pi by 2 is a product of infinitely many numbers. Now, this is something that you will say that I am not able to write infinitely many numbers, how will I have the product? So, this is exactly the strength of mathematics. We can talk about infinite sums and infinite products. So, and these all known numbers that we use daily. So, our engineering cannot work without this trigonometry. Basically, we cannot imagine without pi and log and sine and cos. And these all are results of infinitely many operations, mathematical operations. I'll end with a very small, it's not a very small activity, but somebody who is interested. So, somebody who remembers their 10th grade mathematics and loves geometry can do this activity. So, we are not doing this activity, so you take a circle of diameter 1, it can be 1 centimeter or something, we are not geometry, so it's diameter 1, and inscribe a triangle in it and circumscribe an equilateral triangle in it, around it, and find the perimeter of the two triangles. So, there are two questions. Do the same thing with the square. Inscribe in this circle and circumscribe around the circle, find the perimeter. Do the same thing with the hexagon and do the same thing with the octagon. So what is basically, now you will say that what are you doing? So here what is my aim? Now you see, so sorry, as you go to the octagon, so here it's as you, so you had for the hexagon, you had the octagon, you can see that these are going closer and closer to the circle. And as my n will increase, these n-gons, if I take the regular n-gons that are equal sides, equal length sides, and there are n sides, so that's a regular n-gon, as n will increase, they'll go closer and closer to circle, and the perimeter will come closer and closer to the circumference. And you all know pi is circumference by diameter, and therefore you will have an estimate. So basically as n goes and goes, you will have some numbers, Pn and Pn. And if you go on increasing, you will have something, that numbers approaching to something. And that is exactly pi. So pi, geometrically, how is it a resultant of an infinite operation? You can see, you can have a feel of that. So this was, in fact, this was the way that Archimedes estimated the value of pi. So generally what we estimate the value of pi, 22 by 7. The first thing we are taught is pi is 22 by 7. It's not 22 by 7. It's just an estimate of pi. The circumference by diameter, that's fine. But 22 by 7 is just some value for n. I think it's 96. 96 n gone, 96 gone. That's the value of for that n. It's just an estimate. So I hope, so we'll just end here. Though the discussion and though the knowledge about is infinite, and there's no end to it. Actually, it's infinite. Thank you.
Hello, thank you very much, Professor Jain, for sort of, I hope many of you have been set on the road to infinity, at least by this talk, and I'm sure you have many questions. We'll take a few questions. I hope that's okay. I'd request you to wait till the mic comes to you, and there's a mic there also. So please come to the mic, and please make your question very short and precise and relevant to the talk.
Yeah, I'm Dr. Renuka. I'm an Ayurvedic doctor, but I run a mathematics company for little children. And I'm really feeling great today to see a woman talking about math. It's usually a man's world there. And I'm feeling really great to listen to her. It was wonderful.
Thank you. Okay, question. I think there's a question there.
I just want to ask, with respect to the value of tan 90 and cot 0. It says it's infinity, right? How do you explain that? I mean, if I say value of tan 90 is infinite, what does it mean?
See, the thing is, again, when we are talking of, let us just understand that in terms of infinite, in the context of that, not geometrically, tan x, what is that? So that is some, so I'm just keeping, because I'm just focusing on, so just one aspect of tan. So it's the sum of infinite numbers. As I had shown that sine is the sum of infinite numbers, tan x for any value of x will be a sum of infinite numbers. Now that when you add infinite number, for example, if you're adding, so now that's something that you will be, I don't know whether you will be knowing or not, so but 1 plus 1 by 2 plus 1 by 2 square plus 1 by 3, 1 by 2 cube plus so on is 1. And but 1 plus 2 plus 3 plus 4 plus 5 plus 6, if you go on adding that, you will get something that mathematically you will say, you will have something, not a number. Because if you have first n numbers, it's n plus 1 by 2. As n goes to infinity, you won't get a number. So that we are calling as infinity. So it's becoming large and large as I'm trying to estimate it. That's the thing that I can say here. So it's just signifying that As I want to estimate it, it's becoming larger and larger and larger. That's time 90.
Thank you.
One second. I think there's a question there, and then you can go to the mic, and then, okay.
Yeah. 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 Thank you, ma'am, for throwing some light on a really counterintuitive and sometimes a difficult concept. So my question is, thank you, ma'am, for throwing some light on a topic that can be really counterintuitive to at least to the general audience. So my question is, as a general maths enthusiast who is not very, who is ignorant of the research taking place in maths, so can you give us some examples where all this research on infinity and stuff like that actually happen, and some applications?
Application? See, calculus is the first thing. So you all know, in which grade you are? What are you doing, if you don't mind?
I'm an engineer, mechanical engineer.
So you obviously, then you would be knowing continuous function, differentiability, yes, that you know, slope, all these things. That all is a result of the concept of infinite. There are many aspects to it, but see, just realizing that the set of numbers is infinite is also very important to work. Not only that, but the calculus, everything. So now if I want to have the sum of infinite numbers, if you don't know what is, so first of all you won't accept that there are infinitely many numbers. Okay, if you know that, then you won't accept that there are I can calculate the sum. So there has to be all mathematical notions are developed to actually define. The way I defined what is an infinite set, I can define what is the sum of infinite numbers. Sum of infinitely many numbers. And that leads to, so slowly, basically I'm giving just one example. It's leading to the development of calculus, all these trigonometry, calculus. These are in a way results of the infinite.
Professor, here,
yeah.
Professor, can you give us some idea of how this renormalization which comes in quantum electrodynamics, how it's done, some tricks, is it a trick or is it a mathematical trick or is it really we can divide?
No, there is a physical way to understand it. I mean, since this is a physics question, I'm taking the liberty to answer. But there is a physical way of understanding it in which the infinity is just a sort of an auxiliary object, but people talk of infinities in that context. But actually, by now, there is a much better understanding, and you don't really need to. It is only in some very idealized sense, if you view the problem, that you really encounter infinity. In any actual physical way of defining the problem, you don't encounter infinities, and there is a actual physical, the physical consequences of the idea of renormalization are very measurable and in fact have been experimentally verified. And it is used in quantum electrodynamics, as you said, but also in many other theories of physics, including those of the metals and condensed matter physics.
Is it a real division or is it a trick by mathematicians?
No, it is not a trick. It is an actual phenomenon. But since this is in physics, I won't. I think the questions can be more towards the content of Professor Jain's talk.
One thing I would like to mention, what I've talked about is the more counterintuitive thing. There is a concept, so infinite when we talk of, we can think of two types of, potentially infinite and actually infinite. What I've talked about here is actually infinite. Potentially infinite is something that we basically understand, that it's growing larger and larger.
Yeah.
That is basically that we all in a way use. But yes, one should have an understanding of actually infinite as well to have the distinction between what is infinite, what is finite, what is potentially finite, and all those things. So this is, I've just addressed what is actually infinite. Because potentially infinite we more or less all understand.
This is for, I'm just wanted to ask whether in terms of renormalization theory, is it kind of related to Stelz's integral? In the sense that some infinite quantity, they integrate it with d something, right? And you choose the d, the measuring thing, such that that is also infinite. appropriate
think,
scale?
This question I'm happy to answer separately, but
Okay.
I think since it is not quite, I think the question should be addressed to
So
more the things that are here.
Okay.
But like I answered before, it's not a trick, and
Yeah,
it is
I
an
understand that.
actual
It's like a
physical
fractal, I mean, it's a-
operation. And but I think it's more technical to be able to address in a very quick way like this. And besides, it's not
one
quite-
question. Is C the cardinality of real numbers? Is
Sorry?
C the
Yes.
cardinality of real numbers?
The cardinality of real numbers and the cardinality of line segment is the same. I've just used line segment because more people understand line segment. So we have a more feeling of line segment geometry more than the feeling for real numbers. So.
And if I'm not mistaken, it's still not shown whether there is any infinity between that of the Aleph naught and C, right? Or is it?
The other way, that is C. So you have Aleph naught and Aleph 1.
1, yeah.
So is C between Aleph naught and Aleph 1? That's continuum hypothesis.
Yeah.
Yes.
That's right.
Thank you, ma'am, for the great talk. So I just had one question. Like, how can you say that the number of points in any geometrical figure to say is more than the number of natural numbers?
That basically you will have, so if you understand that, that will require more mathematical technicality. So if you accept that the real numbers are exactly same as the number of line points in the line segment, then I can just tell you a very non-geometric mathematical way. The geometric way, at least I'm not aware of, and it would be very difficult if it's, so it's, but now see, if you take a real number, for example 1.2345667, I can map it to sorry. Oh, sorry. I just got your question wrong. Sorry. So see, you can have points. So in a line segment, you can have points 0.1, 0.11, 0.101. Yes, any decimal which is just consisting of ones and zeros. There are really less than those of all the points in the line segment. And in fact, you can show that these are more than the number of natural numbers. That we can do. That will take a little bit of time. I can tell you after the discussion also separately.
We'll just take one or two questions from the online before coming back to people here. So there's a question, just like pi is a finite number with infinite decimal digits, what is the difference between infinity and unboundedness? That is the question.
See, unboundedness, when we are talking in terms of a distance. So we have the set. And now, does it have a boundary? So, for example, my interval 0, 1 or a line segment is an infinite set, but it is bounded. But my set of natural numbers is an infinite set, which is unbounded. So, infinite sets can be bounded or unbounded, but finite sets are always bounded sets. But the boundedness also needs a notion of a kind of distance strictly speaking, when we talk of bounded thing.
I think the confusion was in that pi is a finite number, but it has a representation in a decimal system with infinitely many digits. So I think they want to, the question is how do you address that, I guess. It's, yeah.
You see, now, just having
I guess just like in the Achilles and the tortoise case, maybe
yeah, exactly.
That might be a
So one very simple thing that when we look at, so I'll give you another example that I think that will be more clear, that will make the answer more clear instead of addressing pi. 0.9999999, just continue with 0.99. There are infinitely many nines. Well, I'm not just stopping at any place. I just write the number 0.99999999. Is it equal to 1? Why is it that? Somebody said yes. Why is it? Exactly. That's the exact. So now, when I'm writing 0.999, if I'm writing 1.1, for example, what is that? 1 plus 1 by 10. So if I'm writing 0.9, that is 9 by 10. What is 0.99? That is 9 by 10 plus 9 by 100. So 0.9999, what would be? It's 9 by 10 plus 9 by 100 plus 9 by 10 power 3 plus 9 by 10 power 4 plus so on. And if you add these infinitely many numbers, we have a finite number. So the concept, now pi is also something like that. I'm adding or multiplying infinitely many numbers, I have a finite number. That is very much possible. As far as boundedness is concerned, that is when we talk of a set. These are very different concepts. Boundedness, a bounded number, I don't have any concept, a bounded number. I have a concept of a bounded set. The two concepts are different. Finite, it's a finite number, that's fine. But it is a result of infinitely many operations. Rational number is not in a way, 1 can be also written as just 1. That's in itself, it's not necessarily an infinite, comes from an infinite operation.
So one more question I'll take from here. Sandeep Kataria, he asks, I remember a few years back, a discovery of largest prime number. How can it help us to understand infinity?
No, that cannot be.
I think he probably means the largest prime number known to humans.
Yes.
That
is a number. Now, in a way, we can say that that is the number. We do not know a bigger prime number than this. That is a prime number for which we do not know a bigger number that is prime. But it cannot be the largest prime number.
It's just a measure of
that
our ignorance.
Euclid 2000 years back showed that we cannot have a largest prime number.
So when people mean largest prime number, it's just largest prime number known to humanity at this point of time.
Yeah.
2 years later, someone may find a larger prime.
Exactly.
And so on. It will never end. But after this person, I'll give the mic then.
Thank you, ma'am, for your talk. I have watched videos where 1 plus 2 plus 3 plus 4 and so on is, the sum is given as minus 1 by 12.
Yes.
How do I understand
So that is
this?
something that, see, now when I'm talking of this sum, and I told somebody that 1 plus 2 plus 3 is going larger and larger and it will go to infinity. That is the sense when I'm in a particular sense. When the usual sense that mathematics defines the sum of infinite numbers. In the usual sense, when I'm talking of sine x is equal to this x minus x cubed by 3 factorial plus x5 by 5 factorial. This is the usual sense when I'm talking of, and in that sense I'm saying that it's going to, but there are different notions of, now that is the word convergence. So in one of the ways I can tell you that it's minus 1 by 12. And in fact, physicists generally consider it to be minus 1 by 12. But it's not the mathematics way. And mathematics also has a notion, but that's not the usual convergence or usual, that we do not address it as a sum of infinitely many numbers. That's not something that we address by that phrase.
Yeah, there's a question here. For,
Madam, what is concept of cardinal numbers?
So cardinal numbers, now when we are talking of the size of the set, so that is the cardinality and the number. So now, for example, if I have 2 elements in the set, so my cardinality will be 2, and that 2 is the cardinal number, that 2 is denoting the size. So now I said that, n cannot be in one-to-one correspondence, so n is an infinite set. So I cannot associate a number which will denote its size if I associate 10 with it. That means it will have 10 elements, but it doesn't have 10 elements. I cannot associate a number with it. So, but still, I want to associate some symbol to it. So, what are numbers? Numbers are also associating the size of certain sets. So, now to basically associate the size of set in finite sets, I am using the symbols LF1, LF2, LF0, all those things. All these numbers 1, 2, all the numbers, all LF0, LF1, these are all cardinal numbers when we are talking of in the way the size of the set, the cardinality or the number of elements of the set. So that is, and when we are talking of the order, when somebody asked that when we are talking of the order, that 4 is greater than less than 5, then we are talking of the order. So in that case, we generally, so now, so there is a definition of numbers that Piano gave, that now we start with 1 and the successor of 1 is 2, successor of 2 is 3, and there are some axioms. So in that case, we are actually going through the order, not the size of the set, and there my numbers are treated as ordinal numbers. So there are also a finite ordinal numbers, that are numbers, 4 is less than 5. Here the order is basically the main focus. And in cardinality, the size is the main focus.
Okay, the next question.
Hello, hello. Yeah, hello. Yeah, ma'am, can you briefly tell about the two expressions 1 by 0 and 0 by 0? And why 1 by 0 is infinity and 0 by 0 is indeterminate?
So 1 by 0, when we say it's infinity, it's basically it's going to infinity. So that's so 1 by x, if I take, as my x goes to 0, this is becoming a larger and larger number. That exactly when I said that infinity. So what do you write? 1 by 0 is infinity, that's horizontal 8. If you write that, what do you mean by that? It's not infinity is not showing you an infinite value, but it is telling you just that as the denominator becomes near and near to 0, my value is becoming bigger and bigger and bigger. It's basically telling me that.
And 0 by 0, he was asking.
0 by 0?
Yeah.
Why it is indeterminate? Why it is indeterminate?
Why is it indeterminate or indefinite?
So now we'll see. If I have 0 by 0 form, so for example, I have, because now that's something that I have myself not very just thought about, but now see, sin x by x, if you are looking at that, that is a 0 by 0 form, but that is 1. On the other hand, if I take x square by x, that is again 0 by 0 form, but that is 0. And if I take x by x square, that is 0 by 0 form, but that is going to infinity. So it's something that cannot be determined.
So
it's something that's not following a certain pattern that I can define.
Ma'am, I believe...
So by 0, at least one can say in a way that it's, if I have 1 by x, as x goes to 0, it will go to infinity.
Yeah, the 0 by 0 case, it will depend on the particular limiting,
yes.
the limiting process that you...
Because we don't like to deal with infinity. It can be minus infinity as x goes to 0 from the negative side.
Yeah.
Yes, yes.
Ma'am, I believe the young man here asked literally $1 million question on the Riemann hypothesis. So ma'am, as someone who's dealing with infinities, what forms or subsets of mathematics would you say make it easier to deal with infinities?
Sorry?
What subsets of mathematics would you say make it easier to deal with infinities? Because I'm sure some of us would like to crack this millennium problem.
What subsets of mathematics? I mean, in
areas.
What areas, I suppose?
Yes, so what I'm aware, Hilbert spaces, for example.
So for Riemann hypothesis?
Yes, ma'am.
So now, see, these are the things that can come in, that depends on, so these are the things that can be, that are addressed by number theorists also, algebraic geometrists also. So that depends on how you see that problem. And I generally do not work on, so complex analysis, this number theory, algebraic geometry, these are the areas that we can really work, deal with. But that's something that's not exactly that, if you're dealing better with infinity or infinite, then you'll be able to deal with Riemann hypothesis. It's not something like that. Infinite, the concept of infinite is basic to all mathematics.
Yeah, I think that is correct.
That's the thing. That
you have to deal with it, whichever area of mathematics you have to, or even physics for that matter. Yeah. So last question, I think.
Madam, you said that for every infinite set, there is an infinite set strictly bigger. Give some example of that, ma'am.
You know the concept of functions?
Yes, ma'am. Yes, ma'am.
If I take the set of natural numbers and I take functions, collection of all functions that I can have from natural numbers to natural numbers. This is a set which has cardinality or which has size strictly bigger than the set of natural numbers. Now on this set I take all the functions, or you know the power set. Power set is a very basic example, and this is the way that we define. So power set functions basically is easier to comprehend, but power set, we take a set and take the collection of all subsets of that set. So the power set always has a size strictly bigger than the original set. And in fact, this is the way that Cantor proved that there are so for every infinite set, I have a bigger infinite set. This is the exact way, by using the power set. It's a very clever, short, interesting mathematics proof. And you just need a little bit of set theory for that.
Thank you.
Okay, I think we'll now close the discussion. But before we go for KAAPI, I want to announce that the next KAAPI with Curiosity, the second anniversary event, is on 14th October. It will be, as I said in the beginning, by Professor Vijayaraghavan, the Principal Scientific Advisor to the Government of India, an eminent biologist. He will talk about science in India, critical and as a critical fulcrum for society. So the poster is there outside, so you can look at the details. And there will be a feedback form because of the second anniversary, so please fill out the, sorry, the title is Science, the Fulcrum for Social and Economic Change. So anyhow, so I invite you all to come for the next KAAPI with Curiosity, and also fill in online our feedback form so that we know what people feel about this event. Before we go out, let's thank Professor Tanvi Jain again for a marvelous talk. So I think she showed how even all of us as finite human beings, we can still dream of the infinite in our minds at least. So thank you very much.